Welcome to Unit 4. In the previous video, we ended our discussion of stoichiometry by talking about reaction yield. Today, we open our new unit focused on solutions. Before we can talk about solutions, we have to discuss mixtures. In chemistry, a mixture is essentially a combination of different substances that do not become chemically bonded as a result of their being combined. This is important to emphasize because a mixture and a compound are not the same thing. A compound, if we remember, is a new substance formed when atoms of more than one element are joined with chemical bonds. New chemical bonds must form for a compound to form. Inside a mixture, though, no new bonds form, so the substances that comprise the mixture keep their chemical identities. This is a lot of technical terms, obviously, but it should all make more sense once we consider some examples of mixtures. Mixtures themselves can be divided into two categories. Homogeneous mixtures are those which appear uniform throughout. Our first example of a homogeneous mixture is air. We might remember from previous science classes that atmospheric air is composed of oxygen gas, nitrogen gas, and other gases in trace amounts. The reason we classify air as a homogeneous mixture is because if we were to somehow take a handful of air and compare it to another handful of air, both handfuls would look exactly the same. This also means that both handfuls would contain the same amounts of nitrogen, oxygen, and the trace gases. Another example of a homogeneous mixture is coffee. Coffee has all sorts of molecules in it. It has caffeine, it has water, it has all sorts of compounds which add flavor, and so on. If we take a spoonful of coffee from a coffee cup and compare it with another spoonful taken from the same cup, both spoonfuls will look exactly the same, and both will contain the same or similar amounts of caffeine, water, and other compounds. This is what makes coffee a homogeneous mixture. On the other hand, we have heterogeneous mixtures. Heterogeneous mixtures do not appear uniform throughout. One example is trail mix. Trail mix usually has bits of different nuts and berries in it, and sometimes it even has pieces of chocolate in it. But the amounts of these different ingredients won't be the same in two handfuls of trail mix. One handful might have more dried cranberries, say, whereas the other has more chocolate. Another example is cereal, any type of breakfast cereal, in milk. We can take 2 spoonfuls from a bowl of cereal and get completely different results. One spoonful might be mostly milk, one might be mostly cereal, and if we took a third, it might have an equal amount of both. These mixtures are not uniform, and for that reason we classify them as heterogeneous. Viewers who have even basic knowledge of Latin roots might also recognize that the prefixes homo and hetero mean same and different respectively, hence the words homogeneous and heterogeneous to describe these two types of mixtures. Now, inside these broad categories we can fit some subdivisions. These subdivisions are based on the sizes of the different substances or particles which are part of a mixture. If the particles are small, we call the resulting mixture a solution. A simple example of a solution is salt dissolved in water. Salt water is water, or H2O, combined with sodium chloride, or NaCl. The salt is completely dissolved in the water, and the salt particles are too small to see with the human eye. In fact, if we were to take a look at a glass of salt water, we wouldn't be able to tell that it was salt water at all. It would just look like water. We also can't separate the salt out of the water using physical means. In other words, we can't just reach into salt water and pull the salt particles out. We would have to evaporate the water by adding heat in order to isolate the sodium chloride. Another example is orange juice. Orange juice, like most fruit juices, is actually mostly water, but the other compounds in the water give it an orange color. We can't see these orange particles, and we also can't separate them using physical means, so we classify orange juice as a solution. Although there is room for clarification here, because an orange juice that contains pulp from the fruit would not be a solution, since the pulp particles are large enough to see. If the particles in a mixture are medium-sized, we call the resulting mixture a colloid. When we say the particles are medium-sized, What we mean is that they are big enough to see with the human eye, but still cannot be separated using physical methods. Mist, for instance, is essentially a mixture of liquid water and air. If we look closely at mist being squeezed from a spray bottle, we'll actually be able to see the water particles as they exit the bottle. But again, we can't easily separate the water from the air. A second, more surprising example is milk. Milk is actually mostly water, just like orange juice, and it contains a lot of fats and proteins floating inside water. If we leave milk out of the fridge, these proteins and fats begin to coagulate, and we can see them. This process is called settling, because the particles gradually settle at the bottom or float to the top of the mixture. At the same time, if we pass milk through a filter, that won't be enough to remove the proteins and fats since the molecules are too small. Compare this with orange juice. We can leave orange juice out for a long time, and if it has no pulp in it, those particles in the orange juice aren't going to coagulate so we can see them. That's the difference between milk and orange juice as mixtures, and that's why the former is a colloid and the latter is a solution. Last but not least, we have suspensions. A suspension is a mixture whose particles are large enough to see and can be separated using purely physical means. Our primary example is salad vinaigrette, which is made up of oil, herbs, and spices in different amounts. We can see these different particles, especially the herbs and oil, just by looking at the vinaigrette, and we can separate these different components using a filter or simply by passing the vinaigrette through a fine mesh sieve. Sand is another example. We can see the different types of powdered rock which comprise sand, and sand itself can be filtered to remove larger pieces of rock from the overall mixture. To make all this easier to remember, here's a little table we can memorize. We have our three types of mixtures over here on the left: solutions, colloids, and suspensions. They are classified based on whether or not the particles are visible and whether or not said particles can be separated. Neither is true for solutions. For colloids, the particles can be seen but not separated. For suspensions, the particles can be both seen and separated. We should also keep in mind that the particles in both colloids and suspensions can settle after some time goes by, but this does not occur in solutions. Put simply, we can evaluate any given mixture by these two criteria up here at the top to determine if it is a solution, a colloid, or a suspension. If it meets neither of these criteria, it's a solution. If it meets one but not the other, it's a colloid. If it meets both of these criteria, it's a suspension. And again, the criterion of being separable assumes that the methods of separation are physical in nature. Physical changes like filtering the mixture are allowed and count toward a mixture being a suspension, but chemical changes like adding another chemical to the mixture do not. It's also important to keep in mind that mixtures can be solids, liquids, or gases, as well as combinations of these different states of matter. We'll put names to some of these combinations later, since we don't want to overload ourselves with too many technical terms too quickly. For now, we just need to remember that solutions are always homogeneous mixtures, whereas colloids and suspensions are always heterogeneous mixtures. However, not all homogeneous mixtures are solutions. Now for our first and only example problem of the day. Example 1 would like us to classify the following substances as A, homogeneous or heterogeneous mixtures, and B, as solutions, colloids, or suspensions. Feel free to pause the video and try this for yourself. This problem really just needs a bit of logical thinking. Let's start with the first substance listed here, mud. What is mud at the end of the day? Mud is fundamentally a mixture of soil and water. We now need to evaluate this mixture on the basis of our two criteria. First of all, are the particles visible? Yes, they are. We can see the soil in mud, That's what gives it a brown color. Our second criteria is being able to separate the particles. We can actually separate water from soil just by letting the mud sit out for a while, because it'll eventually dry out. This meets the second criterion and makes mud a suspension. Because mud is a suspension and all suspensions are heterogeneous mixtures, we can conclude that mud is a heterogeneous mixture. Our second substance is air. We already know that air is homogeneous. One handful of air is exactly the same in terms of composition as another handful of air. But is it a solution? Well, it meets both of our criteria. The particles are both too small to see, and the different gases cannot be separated using purely physical means. So air must be a solution. Number 3 is blood. This can be a bit tricky without some prior science knowledge, but blood is actually mostly plasma, which is a clear liquid that is itself mostly water. The red color of blood comes from the red blood cells, which carry a protein called hemoglobin. In other words, blood is essentially a mixture of red blood cells in plasma. But what about our criteria? Blood is actually a strange case, a trick question if you will. It actually shows traits of both a colloid and a suspension. The particles of blood are visible, especially if it's left out. Dried blood is obviously deprived of the water in plasma, leaving just the red blood cells and whatever other blood cells are floating around in there. But this doesn't happen inside the body, obviously, and the red blood cells themselves aren't exactly easily separated from blood. This means that we can make an argument for blood being either a colloid or a suspension, so both answers are acceptable here. It must be said, however, that oftentimes the default answer is to see blood as a colloid. We can argue for it being a suspension, definitely, but if this is for a test question, classifying it as a colloid is the right answer more often than not. Both colloids and suspensions are heterogeneous mixtures, so blood is heterogeneous. If you're confused on this point, it's important to remember that blood can be pretty easily separated using a process called centrifugation, where the blood is placed in a vial and then put in a machine that spins it around very quickly. This spinning force, or centrifugal force, separates the blood into a layer of plasma on top and a layer of red blood cells and platelets on the bottom. Again, this is an argument for it being a suspension, but this is sort of a trick question, honestly. Our last problem is gravel. This one should be easy enough to figure out. One handful of gravel isn't going to look like another handful, and the particles in gravel are both clearly visible and easily separable. Gravel is therefore a suspension and a heterogeneous mixture. Aside from classifying mixtures based on the size of their component particles, we can also classify colloids specifically based on which states of matter the components are in. An aerosol is when a solid or a liquid is in a mixture inside a gas. An emulsion is when a liquid is inside a solid or a liquid. A foam is when a gas is inside a solid or a liquid. And finally, a sol is when a solid is inside a solid or a liquid. For all these four cases, the substance before the word in, written in yellow, is called the dispersed phase, and the substance after the word in is the dispersion medium. The dispersed phase is said to be dispersed throughout the dispersion medium in a colloid. For this reason, Colloids are sometimes referred to as colloidal dispersions, and the two terms are equivalent. It works a little differently for solutions. A solution has a solute or solutes dissolved in a solvent. A solute is a material being dissolved, whereas the solvent is the material doing the dissolving. In our previous example of salt water, the sodium chloride serves as a solute being dissolved in water, which is the solvent. The terms solute and solvent are also used when we talk about suspensions, even though the solute doesn't really dissolve in a suspension. In salad dressing vinaigrette, for instance, the herbs and spices don't really dissolve in the oil. They are more or less floating around inside it. Even so, we would still call the herbs and spices solutes and the oil the solvent. There are also no special names for solutions or suspensions based on the states of matter the different components are in, so there's no more memorizing to do on that score. We would simply talk about a gaseous solution or a liquid suspension or something along those lines. There aren't really any hard and fast rules for naming solutions as suspensions the way there is with colloids. That's just the way it is in general chemistry. So just remember, the two mixture types beginning with the letter S don't have any special names. Before we close, I wanted to put out my usual reminder that my notes for all of Unit 3 are now available on my personal website for viewing and downloading. I also wanted to mention that these notes are being made available under a Creative Commons license, so be sure to glance over those terms and conditions before using them. I would really appreciate it. In our next video, Unit 4, Video 2, we will introduce molarity. Thank you for watching.